Hello, this video is about a class example on command based amplifier. I made this video because one student asked me for the solution to uh, question one of the homework exercise. So if you have the slide, then you can double check the circuits here. This circuit was copied from the lecturing slide. Uh, the base amplifier has its base bias with R1 and R2. So at DC, the voltage here uh, is not zero. Uh, but at AC, at high frequency, this capacitor becomes conducting, and as a result, this node is going to be grounded at high frequency. And by the same token, we have C1 and C2, they have the same property. At high frequency, they are grounded, but in DC, they are not. And the question asks for voltage gain, uh, input resistance, Rin, yeah, as indicated in here. Yeah, Rin does not involve Rs, and the output resistance, which is to become uh, by looking into here, and it doesn't count RL. So it is important to know. Uh, and another thing is uh, the question does not provide any data about IC, the collected current. And in order to work out all these parameters, we need the um, collected current, but unfortunately, um, we don't have this thing. So what we need to do is we use we work it out. Uh, we work out the DC bias level. So basically, we can treat this circuit. Yeah, we just treat this circuit. We just use this circuit for DC biasing. The rest are open circuit at DC voltage. So now, to begin with, they provide the base emitter voltage as 0.65. So this is 0.65. And we are going to do what we can do is we look at the voltage loop over here. Yeah? You can just go through this loop and apply Kirchhoff's voltage law. So now suppose you have a current here, IE. IE should be very similar to IC. Uh, so we have a voltage here, IE times RE plus 0.65, which is the base emitter voltage. And this value should be equal to VB, the base voltage, the DC voltage for the base. But now there are many ways to solve this problem. There's many ways to find VB, and we are going to take the shortcut and approximate And we can view this point as a point in the voltage divider formed by R1 and R2. So as a result, VB should be equal to V plus minus V minus, and times R2 divided by R1 plus R2. And what else? Uh, and do not forget that this is not zero. This is V minus. So we need to do this. And if you do it, if you substitute all this value into the equation here, what you will get is the DC voltage here will be V6, V6. So it's not zero. And if you want to find the current here, we need to, let me see, I forgot to do that. The I zero, and we need to minus plus V minus is equals to VB. So what we need now is to substitute all this value into this equation. I, E, and then RE 5.6K, and then plus 0.5, and then plus minus 15. And do not forget this value, right? 1.3636. And if you do it carefully, you will find out IE is somewhat equal to 0.002 be one line, yeah, this voltage. And now you have IE. Basically, you can treat this value as the collector current in DC, the last signal collector current. But we want it to be more accurate. So what we need to do is IC is equals to beta minus 1 plus beta times IE. So you have 99 divided by 99 plus 1, and then times this value. There is slight difference. The value that you can get here is 2.2958 millimeter. So with this in mind, we can work out the transconductance, the small signal transconductance, GM. GM is equal to IC divided by the thermal voltage. According to the question, the thermal voltage should be 0.025. So we just substitute the value there. And if you work out carefully, you will get PM, maybe, right? As a start, right? We don't want to make any 0.025. So I expect you will get 0.09182. And You have the IC value, you can use the IC value to work out the conductance. And another thing that you can work it out is the early resistance, R log. So what you can do is R log is equals to VA divided by IC. So if you work out carefully, VA here is 100 and divided by the uh, the current here, the collector current, and you will most likely get 48.557 K. So these are the two values that we need in our uh, small signal analysis. So this is the small signal analysis will be the next step for this exercise. And we need small signal analysis to work out the voltage gain, the input resistance, and the output resistance. So uh, these are the values that we need. Now, based on the circuit here, uh, we can find out the small signal. And to begin with, right, what we need to do is to just remove the red thing. So these are the original circuit. And we are looking for R out here. And R in is to be determined from here. And do not forget this. So now we need to translate this circuit into the small signal equivalent. And we can use high level to do that. So we don't need this, right? We don't need this. The pi model that you need will be somewhat like this. And the signal is to be applied in here. So this is the small signal diagram. And the V pi, the value of V pi is the voltage across the uh, R pi. And because it is connected to the ground, so we may determine that. We determine that, right? The voltage at this node is minus V pi. And the current going into the circuit, let's assume that this is I naught. So basically, right, you have I naught here as well. So to begin with, we need to simplify the circuit. What we can do is we this R pi is connected from base from the emitter to the ground. And we have another resistor, RE, which is connected between the emitter and the ground as well. So what we can do, uh, we can treat them as a parallel. So they can be uh, shorted together. So if I'm going to simplify the circuit, the next thing that I will do is I will just copy the circuit here and VS and RS, and what we need to do is these two are parallel with each other. So at this node, which has a voltage minus V pi, and the resistance here is R pi in parallel with RE. And then we have a network here, and then the current source. This is the dependent current source. And we have a resistance here. So we don't have enough space here. So what we can do is we move up this ground a little bit. And we just draw the current here. And GM V pi. And what we can do is and uh, and then finally we have two resistors connected in parallel, and we can just merge them together without affecting the circuit parameter. So I out. So this one is now. Take a look here. You have a current source connected in parallel with R log. Yeah, they are not physically connected. R log is the small signal early resistance, and they are not measurable. Still, we can model it. So what we can do is we can use testing to testify this parallel combination of the current source GMV pi and uh, R log. So what I'm going to do is I will just do it on the fly. So uh, we just do it on the fly. So what we end up with here is a voltage source. And the voltage source has a value V pi, and analog. And in here, this is analog. So this is already significantly simplified the circuit. What is left now is to further simplify the input because our first goal is to find out the output resistance, the voltage gain. So we can use Lofton technique, Lofton analysis to convert this series connected voltage source and resistance into a current pair, a current source, a pair of current source and a resistance. So what we can do is we convert this uh, into current source. Yes, and RS, and finally we have this so RS. And now it is very obvious. You have two resistors connected in parallel. And what we can do is we just merge them together. So we merge them together into a single unit. So it will be RS in parallel with this resistance, R pi in parallel with RE. So we can do that. We do that now. RS, R, let me see, RS, R pi, and then RE. So it is very obvious. You have a parallel equivalent here. The parallel combination of the current source, and this is the independent current source, and together with the resistance. So we can also terminate this into a series level to make it easy for us to work out the voltage gain. So this now becomes a serious one. And before going forward, let me just emphasize here. You have RS. RS is a very small value, 100. But R pi is usually a very large value. Yeah, about several 48, 40K, something like this. And RE is another large value. So basically, right, we can just assume RS, R pi, RE approximately equal to RS because RS is just 100. So what we can do here is we can just approximate this as this circuit without affecting the accuracy. And now the circuit is much simpler now. What we need to do now is to terminate this pair. So we can do that, right? This one times this one, it become the voltage. Then this is Vs. And now the resistance here will become a series connected resistance. And the loop here remain unchanged. And remember, we are looking for the input resistance and the source voltage is not counted. So in this case, we are expecting to get the input impedance here, and we ignore RS. And down here we will work out the output impedance. We don't want RL, but on the other hand, RC is included. So what I can do now is instead of saying the output impedance here is R out, we can just say R out pump. Yeah. So R pump is different from R out. And at the end, we will work out R pump. We work out the R out by having the parallel equation of R pump and RC. Okay, so all these things can be done. Now we are heading there now. What we need to do now is we work out the voltage gain based on this simplified circuit. And we still have a lot of parameters here, so don't erase that. Right? We will need those parameters. On the other hand, we don't need this circuit, so we remove them. And this one is old-fashioned. So this is the original small signal diagram. Right? Again, we don't need that, so we remove this. So now our work will be based on this parameter. And the first thing that we need is the voltage gain. In order to find the voltage gain, we can just split this into two parts. We find the transfer function up to here, from V out to here, and then from V pi to there. So there's a reason why I chose to do that, because I need the work to work out RE. Yeah, so we just break it down into two half. So uh, first, we have a voltage V out here, and we have another voltage here. So everything becomes very easy. We are going to apply Kirchhoff's voltage law from here to here. Okay? So this is totally doable. We are So we are going to write down the equation. V out is equals to I out times I out times R out naught. And then the voltage here, yeah, is in the opposite direction. Yeah, can you see the plus is in the left side? So we minus Gm V pi, and then R log. And then finally, we don't go further, and we just come up to this point here, yeah, minus V pi. And our job is to find the transfer function. VR divided by V pi first, and then we will do the next thing. And now the important thing that we need to know is the I out, the output voltage, and the output current. So what we can do is we take advantage of the law here, and then work this out. So according to here, the output current, we just look at this little segment here. The output current can be calculated by the voltage and the resistance here. So all we need is to use Ohm's law. VO divided by this resistance. Remember, it is negative. So VO divided by RC RL, yeah, and then oh, oh, and then we can just do simplification on the fly. Yeah, we have V pi in both of the equation. V pi, and then 1 plus GM naught. And I have told you in the lectures, whenever you come across with this expression, then you should know that this value is substantially larger than 1. So in action, you can just uh, rewrite the expression, the equation by doing this. Now, everything becomes downhill now. Why? Because this expression can be moved across, and end up with 1 plus R naught, and then uh, minus V pi Gm R naught. So now another thing that we want is we make this like 1 over R1, 1 over R2. Yeah, we make this as a parallel function. So we divide the equation, both sides of the equation by R log. So we have R log here, cancel out. So we end up with 1 over R log. So basically now it is a parallel network, right? It is equivalent to uh, R log, RC, RL. So you have a GM here, right? We can just move it across. So it is very obvious now. V out over V pi is equals to minus Gm and then a big chunk of expression. And now the next thing that we are planning to do is we work out another transfer function from here to here. So we have minus V pi here. So this is equation 1, right? Let's remember this. Minus V pi is equal to what? IR times RS, and then plus VS. And IR is what? IR, what can you do here? Yeah, we can first use this expression to get V pi and then substitute this into here. So what we have here is V pi minus V pi. So this will become Gm R log RL RC. And then IO divided by OS. So we just simplify the expression, modify VO divided by the CRL, yeah, and then finally we got the VS. So the whole expression becomes substantially easy to handle. And if you move the expression, of course, I'm going to continue here, yeah. Uh, and I don't need this information. Perhaps I need to write down here, yeah. How long is 43.56K? And then GM is 0.0918B2. So I don't need to, I can just free up some space here now. Yeah. So based on what you have here, this the first expression on the right can be moved, of course, to the left, and then we just simplify this. So this is uh, 1 over some kind of resistance and 1 over another kind of resistance. And eventually, you would agree that the transfer function is going to be Vs equals to uh, uh, this parallel with each other, yeah? So RC, RL, did I make any mistake? I hope not. Apparently there is a mistake. Yeah, there is a mistake. RS. So there is a RL here. So we know how to deal with it. We just need to divide it by RS. So it become 1. And then GMRS. EMRS, and then R um, OO, RL, RC. So if this is the case, then finally we can just do this. And if you substitute the numerical value into this formula, then you will finally find the answer 31. And the suggested answer from the question is 30. So this is quite close. And now the input impedance. How are we going to find the input impedance? There is input and output impedance, as we say. We can find the output impedance first. And right now, I have shown you have enough information here. Yeah, this is the way I found the voltage gain AB. But now I'm going to erase this part, and then we will use the failure to calculate the output resistance. And the first thing that we need in, in working out the output resistance is to circuit, short circuit all the independent voltage sources. So we need to find out. We need to short circuit all the independent voltage sources. So, and from there we measure the output, and then work out at the output terminal. So what we need now is to um, sort this. So the next thing that we need is to use another equation, right? So we sort this, yeah, sort this. And then the RO is automatically clear. So what we need is we find out the voltage here first. V out is I out out the voltage here, yeah, and then the minus Gm V pi out, and then the uh, plus I out RS. So this is very clear. And what we need now is to make sure this expression um, become dependent on I out, the output current. So what we need now is we just substitute the value here. So we are make sure we have a clear concept. Minus V out is equals to I out times RS. So we just substitute it there and see what happens. Substitute this one into this equation. So this is equation 1, right? So I suppose this is equation 2. So substitute V pi into 2. So what we have here is V pi I out minus Gm, yeah, passed down. R naught, and then I naught. According to here, yeah, RS. So eventually, everything becomes surprisingly clear. You want to find the output impedance. Then this is the one, output impedance. Uh, RO is equal to VR divided by I out. Uh, and this is equal to R log 1 plus GMRS. So it's surprisingly simple. And if you work this out, we have the 43K here, and then you substitute all these values. And you will find that the output impedance here uh, is 443 and then 557. So the value here, I tell you what, I have to add a palm here. Yeah, palm is 443K. So this is a big value. And what we can do here now, we are very close now. We have this impedance, right? Remember, the output resistance asked by the question include RC. So what we need to do now is uh, take RC into consideration. So R is equal to R death and then RC. So you will be surprised. The answer is 4.29K. Yeah, 4.3K. Okay, so this makes sense. Now you found the output impedance now. The output impedance is just right here. Uh, So how about the input impedance? Input impedance look very tricky because you have the voltage here, and you need to use the voltage and then uh, found the current, and then the voltage divided by the current, and this is the way how we do. But fortunately, uh, you can make our life simple. So what we can do now is to free up this space and then work out the input impedance. Do this. Now again, we are going to use this point. So minus V pi here is equal to this voltage and R naught and minus I out. Um, and then the whole chunk of the impedance. And these two terms can be combined. Yeah, we move this term to the left, to the right. So what we did is 1 plus GM R naught and if you remember our trick, 1 plus GM times R log is essentially GM R log, and then B pi equals to this tranche of expression. I tell you, you don't need to work out anything. Minus I out is equivalent to the input current because they are in series. So R in here is essentially so if I do this, then we will have R log divided by uh, uh, GM R log. So this is simple enough. And according to my calculation, the output impedance, the input resistance here is around 1.774 ohm. The answer from the question is 12 ohm. So from the question, so this is the answer. So they are close enough. I hope I have answered your questions. If you have further questions, please raise your question in the class. Thank you very much.